Greetings, everyone. I am Danilo Botero Lopez, and I am a PhD student in the University of Maine. My advisor is the Professor Aaron Gallant, and today I will be presenting a new analytical methodology that we are developing to evaluate the basal stability of column support embankments, which is a ground improvement technique that is becoming more popular in infrastructure projects in USA and abroad. This system is used to accelerate construction, reducing the stresses in the subsoil via arching, soil-column interface, and tip transfer. This study is motivated due to the limitation of the current design methodology to assess global stability of the column support embankment, which is the same as typical slope stability, as you can see in the figure 1, but consider that the stresses in the columns provide a resisting moment. However, in the first part of this study, in the first phase, we found that column bending resistance didn't influence the magnitude of lateral spreading associated with mobilization of passive resistance at the toe. While column fracturing is a consequence of lateral spreading, the cessation of bending resistance across location doesn't exacerbate this issue. However, assessing the available passive resistance and stability of the foundation materials, in particular the cross, becomes a critical component regarding lateral spreading of and stability of the CSE system. Secondly, it assumes a circular slip surface. And we also show in the first part, the first phase, that typically, the slip surface occurs in the weaker subsoil below the crust at depth for some cases. Some authors have also shown that a slip surface is more akin to a three-wedge mechanism, and that is what we are finding in this new study. Third, there is no physical meaning regarding the stresses between the field, soil, and the columns. As I told you before, the idea of the CSE is to reduce stresses at soil via arching, soil-column interface, and column transfer. Then there is a need to evaluate the factor of safety with physics base in this CSE and overcome all these limitations, which is the goal of this study. Now I'm going to talk about the methodology. We perform 3D final element methods. If I have your attention in figure 2A, this corresponds to the incremental shear strength at the end of the strength reduction analysis in praxis. For one simulation, when the thickness of the crust was 1.5 meters, the field height 8 meters, and column spacing of 2.5. One of the advantages of this final element method is that help to inform us about the slip surface. Furthermore, you can also realize the lateral stresses at the field, like the active pressure, the arching mechanism, the soil-column interface, and the amount of downdrag, the passive resistance, etc. Also, the final element is an excellent tool to analyze the factor of safety of the basal stability. Is very time-consuming. We need a straightforward analytical method to implement in practice, and that is what we are doing. We are developing a method to calculate not only the factor of safety against the basal stability, but also the location of the slip surface. For example, in this case, the red lines indicate the failure slip surface that we are obtaining using our analytical solution. And the other two cases corresponds to column spacing of 2 meters and 1.5 meters. The analytical method is to calculate the factor of safety and the location of the critical slip surface is developed applying lateral equilibrium of the three-wedge system at a fixed Z. And then we proportional reduce the native strength parameters until the equilibrium is found, meaning that the load, it means that the load of the active pressure in the active field and the soil is equal to the resistance, meaning this resistance here and equal to the passive resistance. So that corresponds to our undrained shear strength mobilized, as you can see in the equation 1. Then the factor of safety against basal stability are at depth Z. Remember that we fixed that depth is calculated dividing the mobilized undrained shear strength to cause the imminent equilibrium of the system over the undrained shear strength of the soil. Then you vary the depth of the slip surface and for another Z until obtain your lowest factor of safety, which will correspond to your factor of safety of the soil, of the system, sorry. The novelty of this technique is that we are taking into account the consideration the reduction of the stresses in this part of the soil, in the native soil, due to the arching and the downdraft in the soil. So this is what made this. So we are not considering the columns in the analysis, but we are considering how, like, the reduction of the stresses due to the downdraft in the soil. Let's talk about the results so far. Now, if I focus your attention in figure 3A, I am showing here the analytical solution versus the depth for the case of a spacing of 2.5 meters. As you can see, the factor of safety is greater in the crust due to the high passive resistance. Then there is an abrupt change in the factor of safety that corresponds to the change of the material from a steep soil to a soft clay. We can compare also the shear strengths of the numerical analysis with the analytical solution. And as you can see, the slip surface are between 8 and 10 meters, which is shown here. And this is also, this line is the magnitude of the factor of safety. As you can see, both models, the numerical model and the analytical model, agrees very well. Then we can also compare the two other spacing of 2 meters and 1.5 meters. For the 2 meters also agrees well, but for the 1.5, it doesn't agree well. The reason is that we are assuming an ultimate state in the analytical solution, which means that the columns are fully mobilized all the skin friction, which is not the case for 1.5. So that's why we are having higher stress, high factor of safety. Then if I have your attention in figure 3B, I'm showing there the magnitude of the numerical final elements and the factor of safety of the final elements versus the analytical method. And this is for all the parametric study, where I vary the thickness of the crust, the field height, the column spacing, and the undrained shear strength of the subsoil. And these are there for the factor of safety less than 2. And as you can see, they all have also good agreement. Finally, we are developing an app in MATLAB, which is used to calculate the factor of safety, and you can vary the field height, the column properties, and also the stratigraphy. And you can have these results in really 3 minutes. And for example, you can have the active pressure of the field, the active pressure due to the soil, and also the reduction of the columns, the forces that is a downdraft, and also the passive resistance. You can have everything out there, and you can see here how the factor of safety is varying with depth and where is the critical location. One of the benefits of this work is that it will work like practitioners to calculate factor of safety in a better, straightforward, and also more like very accurate, which also will help to make this design more economic and more efficient. Thank you so much, and I want to acknowledge the DFI and the TIDC for the support, and also to Aaron Galan for the